Have you ever stopped to think about something completely bizarre that happens in your house every single day? Right now, invisible waves are passing through solid walls to bring you the Internet. Your Wi-Fi signal moves through brick, through concrete, through wood, like they are not even there. And yet, you cannot see through those same walls. Light, which is also a wave, bounces right off. Why? What is the difference? Why does one wave pass through and another one stops dead? This is not just a curious observation. This is a window into understanding how the entire universe works. And the answer is going to surprise you, because it has almost nothing to do with what you might think. The answer is going to take us on a journey through the quantum nature of matter, through the dance of electrons, through the very fabric of how waves and particles talk to each other. And along the way, you are going to see that the world is far stranger and more beautiful than it appears. Let us start with what Wi-Fi and light actually are. They are both electromagnetic waves. Same family, same physics, same equations. One is not magic, and the other science. They are siblings, born from the same parent, which is the electromagnetic field that permeates all of space. The only difference between them is their wavelength, which is the distance between one wave peak and the next. Light waves are tiny, incredibly tiny, with wavelengths around 0.5 of a meter. That is smaller than a bacterium. Wi-Fi waves, on the other hand, are huge by comparison, about 12 centimeters from peak to peak. That is the length of your hand. That is a difference of about 200,000 times. Now, here's where it gets interesting. You might think, okay, smaller waves squeeze through gaps and bigger waves cannot. That makes intuitive sense, right? Like water flowing through a crack. But that is exactly backwards. The small waves, the light waves, cannot get through. The big waves, the Wi-Fi waves, sail right through like the wall is not even there. So size alone cannot be the answer. In fact, size is telling us something completely different than what our intuition suggests. Let us do a thought experiment. Imagine you are standing in front of a wall, and you want to understand what happens when a wave hits it. But first, stop thinking of the wall as a solid thing. That is an illusion your eyes give you. Think about what the wall really is at the atomic level. It is a collection of atoms, billions and billions and billions of atoms, all packed together in a lattice, a crystalline or amorphous structure. And each one of those atoms is made of a nucleus, which is tiny and heavy and positively charged, surrounded by a cloud of electrons, which are light and negatively charged and able to move. Here is the key insight. Those electrons can move. They are not frozen in place. They are bound to their atoms, yes, but they can wiggle, they can oscillate. They can be pushed and pulled by forces. And electromagnetic waves are exactly that. They are oscillating electric and magnetic fields. When an electromagnetic wave encounters an atom, the electric field of that wave pushes and pulls on the electrons. It shakes them. It makes them dance. Now, when electrons shake, when they accelerate back and forth, something remarkable happens. This is one of the most beautiful results in all of physics. An accelerating charged particle radiates electromagnetic waves. It becomes a transmitter. It sends out its own waves. So the electron absorbs energy from the incoming wave and then re-radiates it in all directions, not just forward, but backward, sideways, everywhere. So here is what you need to imagine. A light wave comes in and shakes an electron. That electron immediately sends out its own light wave in all directions. But there are not just one or two electrons in a wall. There are billions upon billions of them. Every atom has multiple electrons, and there are more atoms in a cubic centimeter of wall than there are stars in the galaxy. So you have this incomprehensibly large number of little transmitters, all re-radiating waves at once. All these little waves start to interfere with each other, adding up in some places, canceling out in others. It is a symphony of interference. And here is where the wavelength becomes absolutely critical. For light, with its tiny wavelength, here is what happens. Imagine two electrons that are separated by a distance comparable to the wavelength of light, say 0.5 micron apart. When the light wave hits them, they are being pushed by different parts of the wave. One might be at a peak, the other at a trough. They oscillate out of phase with each other. The waves they re-radiate interfere in a very specific way. When you add up all the contributions from all those billions of electrons, something amazing emerges. The re-radiated waves combine to create a strong wave traveling backward, back toward you. That is the reflected wave. That is why you see your reflection in a window, or why a white wall looks bright when you shine light on it. The light bounces back. And what about the waves trying to go forward, deeper into the wall? They interfere destructively. The contributions from different electrons cancel each other out. Almost no light makes it through a thick wall. The energy does not disappear. Some of it is reflected, and some of it is absorbed, turned into heat as the electrons jiggle and collide with atoms. But now, let us think about Wi-Fi. Remember, Wi-Fi waves are huge, 12 centimeters long. When a wave that big hits the wall, it does still shake the electrons. The physics is the same. But here is the beautiful, crucial difference. The electrons in one atom and the electrons in an atom 12 centimeters away, or even just 1 centimeter away, are both being pushed by nearly the same part of the wave at the same time. The wave is so stretched out, so long, that over the distances between atoms, it barely changes. All the electrons in a given region are oscillating almost in sync, almost in phase with each other. When electrons oscillate in sync like that, the waves they re-radiate do not cancel out the forward-traveling wave as effectively. Instead, something else happens. The wave gets slowed down a little bit. It loses some energy, heating up the wall slightly, causing the electrons and atoms to jiggle. But a huge portion of it keeps going. It reconstructs itself on the other side. The wave passes through, not perfectly, not without loss, but substantially. Enough that you can stream a video in your bedroom even though the router is in the living room on the other side of 2 walls. Think about it like this. Imagine you have a long, lazy ocean wave rolling toward a pier with pillars, with support sticking up out of the water. If the wavelength of the wave is much longer than the distance between the pillars, the wave just flows around them and keeps going on the other side. The pillars are an annoyance. They create a little turbulence, but the wave is so big that it does not care. But now imagine a sharp, choppy wave with a wavelength smaller than the spacing between pillars. That wave crashes into the pillars. It breaks up. It scatters. It does not make it through coherently. That is the same principle at work here. But there is another layer to this story, and it is even more surprising. It has to do with resonance. Different materials respond differently to different frequencies, and this is not arbitrary. It is because the electrons in atoms have natural frequencies they prefer to oscillate at. Think of an electron bound to an atom like a ball attached to a spring. If you push it, it will oscillate at a certain frequency, its natural frequency, determined by the mass of the ball and the stiffness of the spring. In the atomic world, the stiffness is determined by the electric force between the electron and the nucleus. When an electromagnetic wave comes in at a frequency close to one of those natural frequencies, something dramatic happens. The electron absorbs the energy very efficiently. It is like pushing a child on a swing at exactly the right rhythm. Each push adds energy, and the swing goes higher and higher. The electron oscillates wildly, and it can even jump to a higher energy level in the atom. This is resonance. And when the electron does this, it takes energy out of the wave. The wave is absorbed. It turns into heat or gets re-radiated in random directions. Either way, the wave does not make it through. For most building materials, the natural resonant frequencies of the electrons are way up in the ultraviolet range or down in the infrared range, near or beyond visible light. So visible light, which sits right in between, interacts strongly with these materials. The electrons respond. They absorb and scatter the light. That is why your wall is opaque to light. The frequencies match up badly, or rather they match up in a way that causes strong interaction. But Wi-Fi frequencies, which are much, much lower, down in the gigahertz range, billions of oscillations per second instead of hundreds of trillions, are nowhere near those resonances. The electrons barely notice the Wi-Fi wave. It is like trying to push a swing at the wrong rhythm. You push and the swing barely moves. The energy is not transferred efficiently. The wave just slides past without much interaction. Now, here is the really wild part, and this is where the story gets philosophical. This means transparency is not a property of the material alone. It is not something intrinsic. It is a relationship. It is a conversation between the material and the frequency of the wave. The same material can be transparent to one wave and opaque to another. Glass is the perfect example. Glass is transparent to visible light because the resonant frequencies of the electrons in silicon dioxide happen to be outside the visible range, up in the ultraviolet. Visible light passes through without much absorption, but shine ultraviolet light on glass and it is opaque. The glass absorbs it. The frequencies match. Your walls are opaque to light, but transparent to Wi-Fi. Your body is opaque to visible light, but somewhat transparent to X-rays. X-rays have even shorter wavelengths than light, even higher frequencies, and even more energy. They are so energetic that they can zip between atoms without interacting much, except when they hit something dense like bone, where the atoms are packed tightly and there are heavy elements with lots of electrons. That is why X-rays show your skeleton. You are not just one thing. You are transparent, opaque, reflective, absorbing, all at once, depending on what kind of wave is looking at you. Reality is not fixed. It is relational. It depends on the question being asked. And here is one more twist, one more layer of complexity. Thickness matters. Even for Wi-Fi, if you make the wall thick enough, eventually the wave will get attenuated. It will lose energy bit by bit, interaction by interaction, until there is nothing left. And if you add certain materials, the game changes completely. Metal, for instance. Metal has free electrons, electrons that are not bound tightly to atoms. They can move freely through the material. When a radio wave like Wi-Fi hits metal, those free electrons respond very strongly. They slosh back and forth like water in a tank. And when they do, they re-radiate the wave very efficiently in the backward direction. Metal reflects Wi-Fi just like a mirror reflects light. That is why you lose signal in an elevator. The metal box reflects the waves back out. That is why basements with metal rebar in the concrete have terrible reception. The metal scatters and reflects the signal. But let us go even deeper. Let us ask why this interference, this adding and canceling of waves, works the way it does. Why does the phase matter so much? This brings us to one of the most profound ideas in physics, which is superposition. Waves are not like particles in the classical sense. They do not just exist at one place with one value. They are spread out. They have amplitude and phase at every point in space. And when two waves meet, they do not collide and bounce off each other. They pass through each other, and their amplitudes add. If two peaks meet, you get a bigger peak. If a peak meets a trough, they cancel. This is superposition. And the phase, the relative timing of the peaks and troughs, is everything. A tiny shift in phase can change constructive interference, where waves add up, into destructive interference, where they cancel. And this phase depends on the distance traveled and the wavelength. If the wavelength is small compared to the distances involved, like light in a wall, the phases are all over the place. Chaos, cancellation. If the wavelength is large, like Wi-Fi, the phases stay similar. Coherence, transmission. This is not just abstract mathematics. This is how the universe works. This is how noise-canceling headphones work. They create a sound wave that is the exact opposite phase of the noise, and the two cancel. This is how holograms work, by recording the phase and amplitude of light. This is how quantum mechanics works, where particles are described by wave functions that interfere with themselves. The principle is universal. Now let us connect this back to Feynman. Richard Feynman had a way of thinking about this that is even more beautiful. He showed that you can think of light, or any electromagnetic wave, as exploring every possible path from the source to the destination. Every single path, no matter how crazy or zigzagged. And each path contributes a little wave, a little amplitude, with a certain phase, and you add them all up. Most of the paths cancel out because their phases are random. But certain paths, the ones where the phases align, those dominate. And for light in free space, those are the straight line paths. But in a material with all those electrons scattering and re-radiating, the story changes. For Wi-Fi, most of the paths through the wall have similar phases because the wavelength is so big. They add up. The wave gets through. For light, the paths have wildly different phases. They cancel. The wave reflects or absorbs. Feynman's path integral formulation shows that this is not just a trick of calculation. This is reality. The wave really does explore all paths, and interference is not a side effect. It is the main event. So the answer to our question, why does Wi-Fi pass through walls but light does not, comes down to this. It is the wavelength. It is the frequency. It is how those waves interact with the electrons in the material. It is about resonance, about phase, about interference. Light waves are small and fast, shaking electrons at just the right frequencies to get absorbed or reflected. The phases of the scattered waves add up to create reflection and absorption. Wi-Fi waves are big and slow, sliding past those same electrons because they are far from resonance, and the phases of the scattered waves stay coherent enough to reconstruct on the other side. But the deepest insight, the one that should make you stop and think, is this. The wall does not know it is a wall. It does not have a label that says opaque or transparent. It only knows how to respond to the wave that is asking the question. Change the wave, and the material changes its behavior. This is true everywhere. The universe does not have fixed properties. It has relationships. What something is depends on what is looking at it, what is interacting with it, and that is the most Feynman thing of all. Reality is not a thing. It is a process. It is an interaction. It is a dance between the question and the answer, between the wave and the matter, between you and the universe. And once you see that, you can never see the world the same way again.